Okay, so welcome back to another video. So here's an interesting number theory problem. We want to find 4 prime factors of the number 3 to the power 32 minus 2 to the power 32 that are less than 100. So, of course, a number like 3 to the 32 minus 2 to the 32, it's going to be a gigantic number for sure. Might be too big to the point that even if you were to plug this to a calculator, you might even just more than likely get it into a form of a scientific notation expansion rather than its, full digit expansion. But all we need to do really is actually, if you can tell from the number itself, we can actually just utilize the difference of squares formulas to actually help break down of our prime factorization technique that we need to find, those prime factors that, of course, that are less than 100. So that's really the trick and technique on how to do this. There's nothing really more I want to add to that because it's a pretty simple number theory problem when I just gave you the explanation and the breakdown of how we're supposed to do this. So to get started, why don't we actually just jump right in with the prime factorization? Well, starting with the difference of squares technique. So 3 to the power 32 minus 2 to the power 32. As mentioned, we're going to utilize the difference of squares formula. So as you can see, we can write this as 3 to the 16 plus 2 to the 16 minus or times 2 to the, or rather, the 3 comes first. What a great start. Times 3 to the 16th minus 2 to the power 16th. Okay, so that's all we can start off with. So why don't we now actually, since we have this, let's actually perform yet another breakdown using the difference of squares formulas. So then 3 to the 16th minus 2 to the 16th is then equal to simply just 3 to the power 8 plus 2 to the power 8 multiplied by 3 to the power 8 minus 2 to the power 8. Same thing again. So guess what? Why don't we actually do that a third time? So 3 to the power 8 minus 2 to the power 8, it's going to be just 3 to the power 4 plus 2 to the power 4 multiplied by 3 to the power 4 minus 2 to the power 4. And yet again, we're going to have to do this again. How many times? This is our 4th time. So 3 to the power 4 minus 2 to the power 4, then it's just simply just going to be 3 square plus 2 square and then multiply by 3 square minus 2 square. And then just for good measure, why the heck not? Why don't we actually do this again just one more time? So 3 square minus 2 square. What is that going to be? Forgot to put the equal sign over here. That's the main important thing. So that is going to be, of course, 3 plus 2 and then multiply by 3 minus 2. And as we know, of course, this is actually just going to be 5 times 1, which that is being 5. So this entire thing over here can be written as the following expansion of, so 3 to the power 16 plus 2 to the power 16. Then we can actually take these up only with the ones that correspond with just the addition. So that means we have then times 3 to the power 8 plus 2 to the power 8 multiplied by 3 to the power 4 plus 2 to the power 4. And then times 3 square plus 2 square and then times 5. So far as we know, 5 is our prime factor, our prime number for the factorization of that big number. So at least we found one of them. So why don't we now in this case, since we have these numbers over here, let's actually break down, find out what are the other prime factorization of these numbers over here too. So that means let's start with the smaller terms. So 3 square plus 5 square. That's a pretty simple calculation to do. So let's see, 3 square plus 2 square. Of course, that's going to be 9 plus 4 is going to be equal to 13. Hey, 13 is indeed a prime number, so at least we found another one of those. So 3 to the power 4 plus 2 to the power 4, then that's going to equal to just 97. Again, another prime number. So that's left with just 3 to the power 8 plus 2 to the power 8, which equals to 6,817. Well, we're kind of unsure if this is considered a prime number or not. So in order to just skip a few steps ahead, we can actually find its prime factorization to show that this is actually going to be 17 times 401. Both of them being prime numbers, of course, but 401 is bigger than 100, so we can actually disregard that. And then we have 17, so at least we found another one of that. So basically, that's really it, because you'll notice that 3 to the 16 plus 2 to the 16, of course, that value itself is obviously going to be bigger than 100. Well, it's, if you were to take its prime factorization out. But if you're actually curious to know like what the value of that is, so why don't we actually just calculate that just for the sake of it. So 316, and then add this with 2 to the power 16, we're going to get that this is 43,112,257, and then skipping some steps ahead, its prime factorization comes down to 3,041 multiplied by 14,177. And of course, as you can tell, those numbers are indeed bigger than 100, so we can actually just disregard those. So that means, let me actually use the red for this. So that means we found actually our 4 prime numbers that actually breaks this down. We have that 5 is one of them, 13 is one of them, 97, and then 17. So the breakdown is that its prime factorization actually comes down to 1, 2, 3, 4, 5, 6, 7, 8. So 4 out of the 8 prime factors that set to equals of this number are strictly or less than 100. I don't need to say strictly, but just less than 100. Did I say 1, 2, 3, 4, 5, 6, 7? I actually meant to say 7 prime factors. 7 prime factors of those is going to equal this, but we only found 4 of the 7 that are strictly less than 100. There you go, I did it again, saying strictly less than. So therefore, our 4 prime numbers that are less than 100 that actually make up this term is simply just going to be 5, 13, 17, and 97. So with that, that concludes our simple little number theory problem of utilizing the prime factorization, but also at the same time utilizing the difference of squares to break this down to help find our prime factors with that. So there you have it. And yeah, that's pretty cool if you ask me.